Okay. So we're going to talk about homeostasis. Now, homeo means kind of the same, and stasis means it means staying the same. And when we talk about homeostasis, we're talking about functions within the body. So it could be, or levels within the body. It could be pH levels, it could be body temperature, it could be blood pressure, and really, yeah, so that's what we're talking about, is keeping those within a healthy range. If we think about, so let's take body temperature for example. Okay, and over here we're going to have, so this is temperature. That's going to be in Fahrenheit. And this will be time in hours. Got 2, 4, 6, 8, 10, 12, 14, 16. Okay. And so if you were to kind of plot this, it kind of start to look like this. So our body temperature, some of it's a little bit higher than what we know as body temperature. We've always been told that 98.6, that's about right there. If you can see, that's kind of right in the middle of everything. Well, our body temperature will actually fluctuate up and down, but our body will compensate for those temperature fluctuations and try to get it back to this midline, which is also called the set point. And it will range within what's called normal range. Now, how the body does this, there's a specific pathway that it uses, and that all starts with a stimulus. So let's keep going with body temperature here. Well, let me show you the pathway first. So there's a stimulus, and then you have a receptor. Now these receptors are usually nerves, or it can also be the endocrine system. So like hormones. And then from reception, or the receptor, there's an afferent. Yeah, afferent. That goes out into the control center. Oh, I'm sorry. This is supposed to be right here. Yeah, the afferent, is sent through the nerves, or the endocrine system, sorry. So then from the control center, you get efferent. Which that's also going to be nerves, or the endocrine system. And then eventually you will have your response from the body. So to show you what this looks like, so let's say the stimulus was a drop in body temperature, so it's cold. The reception is picked up by the nerves and sent through the afferent pathway. Efferent pathway to the control center, which is usually the brain. In this case, it is the brain. Sometimes it can be different with different pathways through the body, but most of the time it's going to be through the brain. From the brain's going to send out through an efferent pathway some type of response, which the response to heat up the body. Well, you got shivering, and you can also have constriction, blood vessels, so specifically in like the hands and feet. And that'll get the blood rushing back to your core so it can stay heated up. And that's the pathway that we hope would eventually, we'll see a rise in body temperature. So to kind of explain this a little bit more, we need to go into, you got negative and positive feedback loops. This is a really good example of a negative feedback loop. So as a rule, negative feedback loops are going to try and they're always going to be pushing towards your set point. They're always going to be trying to return to the set point. And that's what we see here. So they go up and down and up and down, all in an effort to regulate it to that to that set point. Now you have a negative feedback loops. You also have positive feedback loops. Positive feedback loops are a little bit different. So that's when, so this is trying to get back to the set point. This is when it gets further away from the set point. A good example of this is childbirth. So when a woman goes through childbirth, it releases oxytocin. Let me kind of release this. Write some of this right here. So oxytocin is released. Oxytocin is released. That goes to the brain, which elicits a response of uterine contraction, which is trying to push the baby out, and then that puts pressure on the cervix, which pressure on the cervix actually releases oxytocin, more oxytocin. So if we were to draw this on a graph here, and you had, so this is time, and this is oxytocin, and you had, the normal set point, and then a range in between that, your oxytocin would actually start to just go straight up until childbirth. And that's a good example of a positive feedback loop. It will continue to put pressure on the cervix and go back and just release more oxytocin until childbirth is achieved. Okay, I think that's all for positive negative feedback loops and homeostasis. Let's move on here. Okay, now we're going to talk about a little bit of, so we got protein-mediated transport. Protein-mediated transport. First one, we got three things we're going to talk about. We got active transport. We're going to talk about transport through channels, and then carrier mediated transport. Now, when we're talking about transport, we're talking about transport through a cell membrane, or through a membrane. And then you've got passive and active. Passive means that it does not require energy. And it follows its concentration gradient. Or essentially it goes from high concentration of something to low concentration of something. Active transport requires energy, usually in the form of ATP, and it also goes the opposite, so it goes from low concentration to high concentration. And we'll see some examples of that. Active transport is going to go directly to this one, and these two guys, these are passive. So both of these guys, they're going to follow their concentration gradient, so go from high concentration to low concentration. And they don't really require any energy to be put into that. Active transport, well so let's do transport through channels. So we have a couple different channels. First one is just an open channel, it's called a pore. It is specific to the ion, or it is specific to the particle that's going to go through it. So if this one was for sodium, only sodium ions would be able to go through that. They do have another, this one has kind of a cap on it. And when, this one has to do with kind of pressure, not necessarily charge or anything like that, but when the pressure becomes enough inside the cell, this will open like that, and then you'll be able to get ions coming through. Again, it is specific, so if it's for potassium, only potassium will be able to get through. And then you have carrier-mediated transport. Carrier-mediated transport starts with, let me draw this out real quick. Okay, so if this is, let's take sodium again. So sodium, so it's specific to sodium, and when sodium binds to it, it will actually change shape and kind of close off to the outside of the cell. And then it will be able to release that sodium into the intercellular fluid. Again, both of these are passive transport, so they're going from high concentration to low concentration. And that would be for the specific particle. So it would be low for sodium inside and high for sodium on the outside. Okay, let's do a little bit of active transport. Active transport, you have primary and secondary active transport. Let me erase some of this real quick. Okay, so primary active transport, draw another cell here. So primary active transport, it requires ATP, so you need energy in order to do it. Let's say we just have a little protein here. We're going to be able to transfer it in. Let's say we got ATP here, and we've got a sodium, so it's going to be specifically for sodium. You're going to need ATP to go in and bind to that, and then also sodium to bind to that before it will push the sodium out into the extracellular fluid. Now, it will be high concentration out here, and that's the main difference, is there's high concentration out here and low concentration out here. So it's going against its gradient, and it will make it lower in here and higher concentration out here. Now, secondary active transport is actually kind of a result of primary active transport. So because we've got our sodium, because sodium is low in here, your sodium molecules are going to want to come into the cell because it's low. Now, when they do that, other molecules can kind of hitch a ride into the cell, even though, so let's say we have potassium, but potassium is high on the inside. So potassium isn't going to come through on its own without some energy from something else. So let's say we have potassium out here. The potassium will kind of hitch a ride with the sodium through, so then it achieves active transport because it's moving from low to high, whereas sodium is moving with its gradient from high to low. And you can also have the opposite happen. Let's erase that real quick. Where, let's say potassium is actually low inside, and then again our sodium is still low on the inside as well. And you have sodium that will come into the cell, but potassium that will come out of the cell. And that's a couple different ways to do secondary active transport. Now, when this happens, we have a couple things we need to keep in mind, because we do need ATP for this. And without ATP, the pumps won't work at all. So let's say we've got 5 pumps. All right. If we've got 5 ATP, and we'll say these are all for sodium, and then we've got 5 sodium. So as 5 ATP, you're going to find each one of those, and the 5 sodium are going to find each one of those, and then they're going to be able to push out that sodium. But we have something called competition. What happens if there's only 5 sodium, but then you have 50 ATP? There's going to be so much ATP that essentially it gets in the way of these sodiums being able to bind here, so the rate at which sodium will come out will go down until there's nothing left. Now there is something also called saturation. So let's say we've got plenty of ATP now, but what happens if we've got, let's say we've got 1,000 sodium? Well, you've only got 5 pumps. So there's so much sodium that the rate at which it comes out is just going to kind of flatline. And if I draw a graph for you right here, so down here we have concentration. So concentration of sodium. And then here we're going to have the rate at which it's leaving the cell because of those pumps. So it'll do this, and then eventually it'll flatline because you only have a limited amount of pumps, but you have a surplus of sodium, so it won't be able to get through the pumps fast enough. That rate will just flatline and not be able to go anywhere else. I think that's everything we need to talk about that. Okay, let's move on. All right, now we're going to talk about osmolarity. Osmolarity, and first we're going to compare it to molarity. So So the biggest difference is osmolarity. They're both concentrations, but with osmolarity, we're looking at concentrations of particles per 1 liter. For molarity, we're looking for molecules per 1 liter. A good example of this is sodium chloride, right? Now, sodium chloride alone, it's going to be 1 particle and it's going to be 1 molecule. But if we add water, which with permeating through cell membranes, we're going to be doing that a lot. There's water involved. Well, you're going to have your sodium and chloride, those are going to dissociate. You're going to end up with 2. Whereas your molecules are still going to stay the same. You're going to have 1. And that's really important when we think about things entering and going in and out of a cell membrane, because particles, water will follow the greater concentration of particles. And we'll talk about that here in just a second. So now we're using osmolarity and not molarity for that reason when we're talking about cell membranes. So let me erase some of this. We got osmolarity, and now we're going to do kind of osmolarity, and we're going to do tonicity. And I'll give you some examples of each one of these. So there's 3 things that we can have with osmolarity. So it could be isometric. It can be, not isometric. Hypoosmolar. Or isoosmotic, Osmotic. Hypoosmotic. Or hyperosmotic. And then likewise with tonicity, we can have isotonic, you can have hypotonic, you have hypertonic. Oh, I don't know why I capitalized it, but that's what it did. Okay. And basically, to understand this is how I think about iso. Is going to be the same, or I guess you could say like even. Hypo will be less, and hyper is going to be more. So let's say we have a cell here. This is our intercellular fluid. Intercellular fluid is going to be 300 osmol. And that's just a unit that you memorize. Intercellular fluid is going to be 300 osmol. And that's just how that is. Now, with osmolarity, we're still looking at concentration. Tonicity actually has to do with what happens to the cell. So it won't have necessarily a number associated with it. We'll just be able to say, well, it's isotonic, hypotonic, or will be hypertonic after it's done reaching equilibrium through the cell membrane. So an example of isoosmotic. Let me introduce you to a couple things. So we have 0.9%. What is that? Glucose. And then we have 5%. No, sorry, it's the other way around. 0.9% saline and 5% glucose. And both of these come out to be around 300 osmoles. Okay, so if you have a cell or a membrane that you add 9% saline to, that's 300 osmoles. If I do that over here, so we got our 9% saline, well, that's going to be 300 osmoles. And so if you look at those, so let's look at them separately first. So before you add it to the cell. Before you add it to the cell, you have 300 osmoles of a 0.9% saline solution. Okay, we've got that. So we've got 300 osmoles here, we've got 300 osmoles there. That is going to be isotonic. It's the same. Now, if you were to add this to the cell membrane, so we add this over here, because the saline is not able to permeate through the membrane, and there's 300 osmoles, this would be considered isotonic. Nothing would really happen to the cell. It would just exchange water freely. We'll exchange water back and forth at equal rates, so it really wouldn't do much to the cell in terms of tonicity. So it's isotonic. Now, hyperosmotic or hypoosmotic, that would be if let's say we halved this. So we said we have 150 osmoles. Because this is less than what's going to be in here, we're going to say we have a hypoosmotic solution. And then when we add this to the cell, so remember it's in terms of the cell, we're going to do it in terms of the cell to the solution. So what happens to the cell if you have a 150 osmolar solution? Well, remember, water will follow the greater concentration of particles, whereas the greater concentration is going to be in the cell. So our water is going to try and want to even that out. So it's going to go into the cell until it becomes even, and we're going to have a hypertonic cell. So the cell in relation to the solution that we put in is going to be hypertonic. Now, hyperosmotic, if you were to change that, and we don't have 150, but instead we did 600. 600. Well, now we have 600 on the outside here. So 600 compared to the 300, that's going to be our hyperosmotic. Hyperosmotic, so there's more concentration on the outside than there's on the inside. When we put that in here in relation to the cell, so what's going to happen to the cell? Well, our water follows the greater concentration, so it's going to come out. It's going to come out, and this is going to be able to become hypotonic. Now, that was just with saline. Just think about glucose for a minute. Glucose, when you add glucose to a cell, the glucose will actually be able to permeate through that membrane. It's let through pretty easily, but it will also metabolize. So that glucose is essentially going to go to the middle and disappear. And this is how we can actually get a solution that is hyperosmotic, but turns out to be isotonic. And let me show you how that works real quick. Let me erase some of this. Okay. Let's say we got our solution over here. Let's say we've got a solution of 5% glucose and 0.9% saline. Okay? So that's what we've got. So essentially that comes out, it's 300 and 300. So it's all together it's going to be 600. Well, compare that to the intercellular fluid of the 300. What are we at? We're hyperosmotic. Not hypo, sorry. Hyperosmotic. Well, let's put that into the cell. So we've got our 0.9% saline. But that is going to go, sorry, not that. But our glucose, so we got our 5% glucose. That's going to go straight to the cell, right? And that's going to metabolize, essentially, it's going to disappear. It's not going to be there anymore. Well, you had, this was 300, that went straight to the cell, and then, got metabolized. This is 300, it stayed on the outside. So if this gets metabolized, it's no longer there, and we end up with 300 osmolar in the intercellular fluid, and 300 osmolar in the extracellular fluid. So we started out hyperosmotic here with 600 osmoles, but we ended up isotonic with 300 and 300 on each side. And that's pretty much all you need to know about that. Fantastic.